Good day, doctor. So today, doctor, as you can see, I and my group has come here before you to present or to do a short video regarding our application of engineering. So this is our assignment 2, and as you can see, we have 4 people in our group, including me, Jonathan Jose, SREE ARAN, CHEE, and NORAZLINA. So without further wasting time, let's go to our learning outcome. So for our learning outcome, what can we gain from this? Recognize when a function of 2 variables is integratable over a rectangular region. Recognize and use some of the properties of double integral. Evaluate a double integral over a region by writing it as an iterated integral. Use a double integral to calculate the area of a region, volume under a surface, or average value of a function over a plane region. So by looking at this learning outcome, I bet doctor already know what we are going to do. So today we are going to be doing, our title is double integral, and our application is thin plate and or LAMINA. So introduction of double integral. First, let's go and see the definition of a double integral. The definite integral can be extended of 2 functions of more than 1 variable. Consider, for example, a function of 2 variables z equals f(xy). The double integral of function f(xy) is denoted by where R is the region of integrated in the xy plane. As doctor can see over here, this is the definition of double integral. Moving on. Why do we use double integral? In mathematics, an integral assigns numbers to function in a way that can describe displacement, area, volume, and other concepts that arise by combining infinitesimal data. The process of finding integral is called integration. Along with differentiation, integration is a fundamental operation of calculus and serves as a tool to solve problems in mathematics and physics involving the area of arbitrary shape, the length of a curve, the volume of a solid, and among others. How to understand double integral with formula? As you know, formula is a key aspect in double integral. So with that, given a 2 variable of function f(xy), you can find a volume between this graph and a region of the xy plane. By taking an integral of an integral, this is called double integral. You can compute this same volume by changing the order of integration. So you can see the first picture from your left hand side. You can see they are in the bracket is dx, making this a function of y, whereas the picture on your right hand side is dy. We're making this the function of x. No need to worry, the computation will look and feel a bit different, but it still gives the same results. Now let's go on a short example of integral, double integral. Okay, as you can see, D is a region bounded by the picture, the graph. So we have 2 curve, which is y equals square root of x and y equals x power cube, x power of 3. So as you can see, this is the curve, whereas this is the function 4xy minus y3. So how do you solve it? It's easy to solve double integration. First, we put the limits between the x-axis and y-axis. As you know, the x-axis over here is x3 to square root of x, and the x-axis, the x-plane, is from 0 to 1. So you will do dy dx, meaning you will you will integrate dy, and you will later on integrate dx. So by doing this, by putting 4xy minus y3 dy dx, you will get the answer of 55/156. So doctor, this is the application of double integral will be explained by my friend SREE ARAN. Thank you, doctor.
Getting to Dr. SUBRAMANIAM. So basically, as Jonathan already explained about the introduction regarding what is Dr. about, I myself a doctor. I'll be explaining about the application of Dr. in thin plate and lamina. So basically, I just like to give a view that how can you use them in real life and how does this concept contributes to real life engineering applications. So basically, in mathematics, a planar lamina is closed surface of a mass and a surface density such as the closed surface, and this is the given equation. Okay, so basically planar laminas can be used to compute many things such as mass, electric charge and moments of inertia or center of mass. In double integral we can consider a lamina with a variable density. So this is what basically it defines. Okay, so next slide. So basically, density and mass. Okay, how do we apply this in our daily life application for engineering? Is this density and mass is basically the lamina occupies a region of D of XY plane, and intensity at a point that x and y in D is given by a continuous function. So the delta m, delta a are the mass and area of a small rectangle that contains specified coordinate, and the limit is taken as the dimension of the rectangle approaches 0. Therefore, we arrive at the definition of total mass in the lamina. This is to find a total mass. So also we can consider that physics also says that the other type of density can be treated the same manner, finding the same way to know other things such as electrical charge is distributed over a specified region D, and the charge density we can find that. Okay, so as I explained here, and the total charge equation is basically this one. The next basically is the moment of center of mass, is basically where is the mass of the lamina. So we should know why we are finding this and how does it help us to contribute in engineering application. So the center of mass of lamina with the density function that occupies a region D, like over here. Okay, to find the center of mass we first have to find the moment of a particle about an axis which is defined as a product of its mass and its directed distance from the. That's how it works. Okay, one more thing we also should understand, the reason why we need to find how does it help us in real life application is this thing happens that the physical significance is that lamina behave as if its entire mass is concentrated at its center of mass. So therefore the lamina balances horizontally when supported in a center. So basically we can use these applications to understand that a lamina will balance horizontally when it has a supported center of mass. Okay, coming to the end, I'll just wrap up here the moment of inertia. So the moment of inertia, also called the second moment of a particle of a mass m upon axis, is defined to be mr square, where the r is a distance from a particle of the axis which extends to construct to a lamina with the density function and occupy the region D as it is coordinate moment. Simple as that. Basically, the parameters that should be considered as moment of inertia about the x-axis, moment of inertia about the y-axis, and also moment of inertia about the origin. Simple as that, and you can see the formulas listed out here. So this is a simple example here where moment of inertia, and the angular mass, where the particle is moving, and we calculate the angular momentum for the engine application, where I explain the next slide. Okay, so as you can see here, I just explained the moment inertia of the disc above the origin, like a wheel above its axle, can be written as the formula shown below. So basically what I mean by here is, this is the application I was regarding to. So if we increase the mass of the radius of the disc, where we thereby also increase the moment of inertia. So this is explained in a braking system of a car, where in general the moment of inertia plays much the same role in the rotation motion that mass plays in any motion. So the motion of the inertia of a wheel is what it makes it difficult to start or stop the rotation of the wheel. Is this is same as the mass of the car is what makes it difficult to start or stop the motion of the car. So that's all from me. Thank you.
Good day, Doctor. I'm CHEE. Now I'm presenting for the question and also the solution for this assignment. The full working of this solution will be sent in PDF form via ULearn. Now, looking at our question. Our question is about Steven bought a thin triangular iron plate for his house for construction. The thin plate was set in an inertial position while having a 2 meter in height and also 1 meter in length. So the triangular iron plate has a density of 1 plus 3x plus y. Okay, fine. The the area of the plate by using double integral approach. B. Find the first moment of the lamina. C. Find the center of mass. D. Locate the center of gravity. And E is about find the moment of inertia. So now I will be talk about question A and B. Then my friend will talk about C, D, E later. Okay. First of all, we sketch out the graph by using the information given at here. Okay, we have 2 meter in height and also 1 meter in length, meaning that here will be 2 meter is the height and here will be the length, which is 1 meter. Okay, here will be the region for us to use for each of the question later. Okay, now for question A is about the area of the plate by using double integral approach. So the formula we use is double integral of 1 dA. Okay, before that we need to find the function for this straight line. Okay, so the formula for find the y function, the straight line, is y equals to mx plus c. So after that we will get gradient and also the c-intercept. So we will get our y function. Okay, after that we use this area formula. Okay, we decide to integrate the y first, then only x. So meaning that the inner integral will be our y. So from 0 to 2 minus 2x. And then the outer integral will be our x. So we're from 0 to 1. Then we integrate the inner integral, then outer integral, then we'll get our area is 1. Okay, for the next question is the moment of the lamina. So meaning we have 2 formula used. One is for moment about x-axis, one is about the moment of y-axis. Okay, for mx, we will use double integral of y rho xy dA. So for moment about y-axis, actually is almost the same with the mx. Just the difference is at here. We use x rho xy dA. Okay, so for find the x-axis, the moment for x-axis first. So what is the function of rho xy? Actually is given in the question, which is 1 plus 3x plus y. Okay, so we sub in this function for rho xy. Then the limit of y and also the x is also the same as the previous one, which is our area, the limit we use. So we integrate the inner integral, then we continue to integrate our outer integral, then we'll get our mx is 11 over 6. Okay, so for the moment about y-axis, it's actually the same. We substitute this, we replace this y to x, and then the rho function is still the same. The limit for x-axis and y-axis also the same. So we integrate for the inner one, then we integrate for the outer one, then we'll get our moment about y-axis is 1. Okay, that's all from me. Now I will pass to my friend to talk about the C, D, E question. Thank you, doctor.
Hello, I'm Auni. So now let me to explain to you how we find the center of mass. Okay, but before that, in previous question, we find the first moment of the lamina, which is moment about x-axis and moment about y-axis. So we use the value to put in the formula center of mass. Okay, so what the formula center of mass? Okay, so the formula center of mass is S bar equal to the moment about y-axis divided by m, which is m mass, and the other one y bar equal to the moment about x-axis divided by m. Okay, before we use the formula, we must know the value of m, which is mass. So the formula of m is m equal to double integral psy, which is density function, and dA dy dx. So in our case, we know the region is 0 to 2 minus 2s and 0 to 1. Okay, so we do the calculation and get the answer. Okay, after we know all the value, okay, so we put the value at the formula x bar equal to the my divided by m, and the other one y bar equal to the ms divided by m. So we do the calculation and get the answer. Okay, next Okay, next question is locate the center of gravity. After we know the answer of center of mass, we can plot the graph. Okay. Okay, last question is moment of lamina. So they have a two, which is moment of inertia about the x-axis and moment of inertia about the y-axis. So the formula we use is IS equal to double integral y2 psy dy dx, and the other one I1 equal to double integral x2 psy dy dx. Okay, so now moment of inertia about the x-axis. So we know the IS equal to double integral y2 psy dy dx. So in our case, we know the region value is 0 to minus 2s and 0 to 1. y2 is constant and psy is density function, which is 1 plus 3s plus y and dy dx. So you do the calculation and get the answer 28 over 15, or the decimal answer 1.8667. Okay, actually, moment of inertia about the y-axis calculation is similar to the moment of inertia about the x-axis. So the difference is formula I1 equal to the double integral x2 psy dy dx. Okay, so do the calculation and get the answer 8 over 250, or the decimal answer 0.5333. Okay. Okay, Doctor, before I stop with the presentation, I would like to remind Doctor that the question and working, which clearly shows step by step, is going to be given or had been given by PDF to Doctor. Doctor, thank you from my teammates and goodbye.